Okay, welcome back. So this is going to be part 3 of the lecture on exponential growth and decay. So this is going to be, we're going to derive a formula for continuously compounded interest. But before I tell you what that is, I'm going to remind you of what compound interest means. So suppose you make an investment of an amount, A0, at an annual interest rate, R. And suppose that interest is compounded N times per year. So that means N times a year, the annual interest rate is divided by N, and then that amount of interest is computed on your investment and added to your investment. So then the next time it's computed, the interest is computed on a larger amount, and it's done N times a year. So let's see what that formula looks like. So after T years, you're going to have A of T is going to be your original amount, the initial investment, A0, times 1 plus the interest rate divided by N raised to the NT. And this is called the compound interest formula. So you probably learned this formula in algebra, maybe again in pre-calculus. You got to see how it was derived. It's very easy, very simple to derive. So let's look at a couple of examples of how to use this formula. So suppose you're investing $10,000 at 5% per year. So let's get a formula for how much you'll have if you're compounding it quarterly. So compounded quarterly after T years, you'll have A of T will be 10,000 times 1 plus 0.05 divided by 4 raised to the 4 times T. That's 4 times a year. Quarterly means 4 times every year. So what if you compound it monthly? Monthly means 12 times a year. So you're compounding the interest more frequently, but you're dividing that interest rate by 12 when you're computing the interest. So let's see what that formula would look like. After T years, you'll have A of T will be 10,000 times 1 plus 0.05 divided by 12 raised to the 12T, and that's 12 times a year. So it's similar, it's hard to tell. We're taking a smaller number. 1 plus 0.05 divided by 12 is a smaller number than 1 plus 0.05 divided by 4, but we're raising it to a higher power. 12 times T is a larger number than 4 times T. So let's just look at a specific example of what happens to our $10,000 after 10 years. So after 10 years using the quarterly compounding, if we plug in 10 and do all the computation on the calculator, we would end up with, after 10 years, we'd have $16,436.19. That's pretty good. So let's see, if we compound it monthly after 10 years, how much we'll have. Put it into the calculator. A of 10 using the second formula turns out to be $16,470.09. So that's a difference of about $35. It's actually more. If you compound it monthly, you'll end up with $35 more than if you compounded it quarterly. So it is true that the more frequently you compound the interest, the more quickly your money will grow. So continuous compounding is like the most frequent we could possibly compound our interest. So for continuous compounding, what we do is we let the frequency approach infinity. We let n approach infinity. Now this isn't actually possible to do, so this is theoretical, but it's used in a lot of financial applications, the theory behind continuous compounding. So let's look at what the formula would look like if we let n go to infinity. So a of t would be the limit as a approaches infinity of a0 times 1 plus r over n raised to the nt. So let's use what we know about limit laws. But first of all, what I'm going to do is I'm going to rewrite that exponent, n times t, I'm going to rewrite it as n over r times rt. Okay, so I just rewrote nt as n over r times rt. And you're wondering, why am I doing this? But you'll see in a minute. Notice I now have 1 plus r over n, and then the exponent is the reciprocal. It's n over r. So that's the key. So what we're going to do is make a substitution. Let's let m be n over r. And then m will approach infinity as n approaches infinity. So we can make the substitution, and the limit will be the limit as m approaches infinity of a0 times 1 plus 1 over m raised to the m, and all of that raised to the rt. And now let's use some limit laws. I can pull that a0 out. That's just a constant. So it's a0 times the limit. And now, because 1 plus 1 over m raised to the m is a continuous function, what I also did was I brought the limit inside. Notice that there's brackets around the limit, and the whole limit is now being raised to the r times t. I'm using continuity to be able to do that. And now the limit should look familiar to you. We recently learned that that limit is a new way to define the number e. The limit as m approaches infinity of 1 plus 1 over m raised to the m is a new way to define e that we learned just before the exam. And so now the formula looks like this. A of t is equal to the initial investment, a naught, times e to the rt. A nice, simple, clean formula. And this is called the continuously compounded interest formula. So what would happen to our $10,000 after 10 years if we compounded continuously? So after 10 years, our $10,000 investment will be worth A of t equals 10,000 times e to the 0.05 times 10. I put that in my calculator, and I got $16,487.21. It's about $17 more than the amount we got when we compounded monthly. And this is the best we can do. There's no way we could compound interest any more frequently than this. So this will maximize our investment. And that's it for section 3.8. So I'm now going to do a couple of videos on related rates. I think I have 2 or 3 videos coming. Related rates, that's section 3.9.